Okay, on the lesson today, these are the notes that were taken on October 21st on the page 8 of your gas packet. This is the gas packet that has the problems that we've been working. We're going to start this day off. We're going to do a couple of things. We're going to work on gas stoichiometry and Dalton's law, partial pressures, and a little bit about partial pressures with respect to mole fraction. Then we'll finish up with problems about how to do gas stoichiometry when you are collecting a gas over water. Now I'm going to start off by saying that you did a little bit of this last year in pre-AP and academic chemistry, and you did some gas stoich when you also did your plane stoichiometry. So I'm going to kind of break this into two pieces. One is gas stoichiometry at STP. Okay. You are going to have to know how to use the ideal gas law, then quantities where you are at STP and where you are not. At STP, remember that 1 mole is equal to 22.4 liters of a gas. Remember, this has to be a gas, and that is actually in your formula chart. Ideal gas at STP is 22.4 liters per mole. So let's look at this problem. It says a sample of nitrogen gas has a volume of 1.75 liters at STP. How many moles of nitrogen are present? Now remember that STP has two pieces of information, 0 degrees C and 1 atmosphere, right? So those two pieces of information, and actually, yes, that is on your chart too. Actually, it's given in Kelvin. So it's 273.15 Kelvin. That is data also. So it says you have this sample of nitrogen in a volume of 1.75 at 273 and 1 atmosphere. How many moles are present? Well, given this, I'm going to work it two ways. The first way, easy, I'm just going to do a little Pivnert problem, right? PV equals nRT, N times 0.821. Remember that I'm going to find the R value that I need based on my pressure unit. Now I've rounded this to 0.0821 in my problems. Okay, since this is in atmospheres, then I'm going to use the R value that is in atmospheres. Okay, and then I multiply that by 273.15 K, and I solve for N, and N turns out to be 7.80 times 10 to the minus 2 moles. Now, that's good, but there's another way I can do this. I'm at standard temperature and pressure. So if I want to, I could just use the relationship that 22.4 liters of N2 is 1 mole, and that is also 7.80 times 10 to the minus 2 moles. At STP, I can do it either way. I cannot use number 2 if my conditions are not at standard temperature and pressure. Okay, now let's look at the next problem. You can do this problem. You did many problems like this even last year. Quicklime is produced by the thermal decomposition of calcium carbonate. Calculate the volume at STP. There we are. Produced from the decomposition of 152 grams of this by the reaction. So what I want to do is I want to find out how much of this in liters do I have. This is exactly what we did last year. Because we are at STP, all we have to use is stoichiometry. So I'm going to start this by taking my given and putting it over 1. I'm then going to drop my unit, grams, calcium carbonate, to mole calcium carbonate, We know that 100.1 grams is 1 mole. I'm going to drop mole because what do I want again? I want liters of carbon dioxide. So I got to go to moles, then to liters. So I'm going to go from moles, calcium carbonate, which is 1, because remember I have a 1 here and a 1 here, and 1 mole of carbon dioxide. So that gives me moles carbon dioxide to liters carbon dioxide is 22.4, and that turns out to be 34.1 liters carbon dioxide at STP. Okay. Now, if I'm not at STP, I'm going to have to find a different way to do this. Now, this problem is going to be a lot like what you did last year, only we're going to add a little bit to it. This has got a lot of data in it. So one of the things you want to do when you have this many numbers is organize your data. Make sure you know what goes with what, because it's a lot of numbers. 1, 2, 3, 4, 5, 6, 7, 8 pieces of data. So what I'm going to do is I'm going to find a way to organize it. So let's read the problem. A sample of methane gas having a volume of 2.8 liters at 25 degrees C and 1.65 atmospheres was mixed with a sample of oxygen gas having a volume of 35 liters at 31 degrees C and 1.25 atmospheres. The mixture was then ignited to form carbon dioxide and water. Calculate the volume of CO2 formed at a pressure of 2.5 atmospheres and a temperature of 125. Well, the first thing I want to do is I'm going to write out the equation. Because obviously I've got methane and I'm going to carbon dioxide. So let's look and see how this happens. I'm going to write out my equation. I'm going to balance, and that gives me that. Now, the next thing I want to do, just like we did up here, where we write our quantities under each species to kind of figure out where we're going, let's do the same here. Let's organize everything. So this says I have 2.80 liters. I have it at 298.15 K, and it's at 1.65 atmospheres. Oxygen I have at 35 liters, 304.15 degrees K, and 1.25 atmospheres. And I'm going to go to some volume. I don't know what this volume is, but I know that my carbon dioxide is at 398 K and 2.5 atmospheres. So this is where I want to go. So if you look at this, should remind you of when we used to say something like, I have 2 grams of methane and 5 grams of oxygen. How much CO2 would I make? This is a limiting reagent problem. Only my quantities are in terms of gas variables, not mass. So what do I want to do? I want to get to mass, and the closest I can do, I could even get to moles. So what I'm going to do is I'm going to use each of these set of conditions, convert them to moles, find out how many moles of this I have, which I can then go on and calculate liters. So in this gas stoichiometry problem, it's going to be Pivnert first, then Stoich, right? So I'm going to shortcut it a little bit. The number of moles of methane is going to be PV over RT. That's going to be 1.65 times 2.80. I'm just taking all this data, dumping it into Pivnert, 0821, 298.15. That gives me 0.189 moles methane. But that's not what I want, right? What is it I want? I want moles of CO2 so I can get moles of volume. So let's go on one step further. 1 mole of CH4 is going to 1 mole of carbon dioxide and that equals 0.189 moles carbon dioxide. Okay, let's do the second one. Remember, when we do a limiting reagent problem, we go reactant to product, reactant to product. This is 1, this is 2. So let's go on to the next one. NO2 is equal to PV over RT, which is 1.25 times 35.0 divided by 0.0821 times 304. That's going to be 1.75 moles. And what I want, this is of O2. And then I'm going to do 2 mole O2 to 1 mole of CO2. And that equals 0.8. I believe that, let me check this real quick. 1.75 divided by 2. Yes, 0.88 mole CO2. All right, as we always do in limiting reagents, this is the smallest one. Methane is my limiting reagent. So this is only the amount of carbon dioxide that I can make. So I'm going to take PV equals nRT. I'm going to solve for V, which would be nRT over P, which is going to be 0.189 times 0.0821. Remember, R is going to be in atmospheres because that is the unit that I have in the problem. So that's my R value. 398 divided by 2.5, and I get 2.47 liters. Okay. Now, there are going to be times where you're going to be asked, this is pretty useful actually, how to use PivNert to solve for molar mass using mass or density. And so what I'm going to do is I'm going to show you how to rearrange this PivNert equation so that you can do that. Now, 1, PV is equal to nRT, and N is equal to mass over molar mass. And if you look at your formula chart, here they are. Don't confuse this M with molarity, right? Because it's here, but this is molar mass. So what that means is that if I want to substitute, I can substitute N, and what I will get is PV is equal to little m over molar mass times RT. Now, what I want to do is I want to get molar mass by itself, so I'm going to cross multiply. We're going to put this over here. PV times M is equal to little m RT. I'm going to divide both sides by PV, and that gives me big M is equal to little m RT divided by PV. Now notice something else here, and that is, what is mass divided by volume? Mass divided by volume is also on your formula chart. There it is, it's density. So this is equal to dRT divided by P. So let's work our first problem. The density of a gas was measured at 1.5 atmospheres and 27 degrees Celsius and found to be 1.95 grams per liter. Calculate the molar mass. Well, that's easy. I'm just going to plug everything into this equation. M is 1.95 times 0.821 times 300.15. Remember, I have to put this into